All right, here we are on our journey for normalization. All right, where do we start? Well, we basically start talking about redundancy because at the crux of almost all the normalization is the idea that we've got redundancy in our database design, and that's going to lead to problems. Basically, we could subtitle this redundancy is evil in databases. All right. So what do we mean by redundancy? Redundancy is basically that we are storing the same information in more than one place in our database. Okay. This leads to some issues. That's just why it would be evil, is that, well, sort of the obvious is it wastes space. You don't care about this because your databases aren't huge yet. You go work for Walmart, you sure don't want to waste space at Walmart, their database that manages basically this gigantic system of all the stores in the supply chain. They're gigantic. Same thing, any of these other mega firms, the databases are huge. You don't want to be wasting space. Wasted space leads to things being slow and more expensive. Anyways, but the real problem is that redundancy leads to you having update, insert, and delete anomalies. It's not quite like Star Trek, we have a space-time continuum anomaly. No, it's not. These are, sorry, that's not funny. Anyway, update, insert, and delete anomalies. Basically, we're going to have problems with these. What does this mean? All right. When we have an update anomaly, our issue is that we must update multiple locations. Because again, we've put the data in all sorts of places in the database. We've got to do it all at once. And we are very likely to miss some. So, oh, I didn't realize I had it over there. And we've talked about this even with like, this is one of the great downsides of a natural primary key. If we are not confident that that primary key is not going to change, because the primary key gets used in all these joins and all these relationships and stuff, we would have to go and hunt down and find all of those, the primary key that we're changing, and fix them all. Otherwise, we break the database. But there's other notions of this. It's not just for primary keys. It's for other arrangements of data, and we'll see this in a moment. We certainly don't want to have this. It makes updating very difficult and leads to us making mistakes. Insert anomalies. Well, this is the idea that we might need to insert unrelated data to insert something. So it's basically, oh, I want to just put this in the database. Oh, but to put it in the database, I also have to put this stuff in there. And we'll see that usually this is tied to the notions that we've got what are known as dependencies, and dependencies lead to redundancy. And finally, a delete anomaly is very similar. You might have to delete more than you might want to. So in other words, we want to delete one thing, but we actually end up having to delete a bunch of other data as well to get rid of it, and that could be really problematic. So let's look at an example here, and this comes from the Cow book. So we go ahead and they've got a relation, employees. This is actually modified from the cow book, but each employee has an ID, a name. They have some level. This is assigned to them that, oh, you work at this level in the company. They have, for a given level, they have, I'm not going to call it hourly. I'm going to make it just wages, so I don't have to write as much, but you can think of it, this is how much we get paid per hour. And then, for example, how many hours a week does the person work? All right. Where, our ID here would be our primary key. Now, the thing that we have here is that level determines wages. So in this company that we're modeling, if you're a level 5, you're going to make $15 an hour. Okay, you're level 8, you're going to make $21 an hour. So the level determines the wages. And so basically, this ends up being an example of a functional dependency. And this is our biggest thing to be concerned about when we're talking about all of these normal forms. If we can eliminate all the bad functional dependencies, we can get ourselves to Boyce-Codd normal form. Then there's this other thing called multi-valued dependencies that we need to take care of to get to the fourth normal form. I'm not going to bother to talk about them. Getting to Boyce-Codd normal form is great, and this is probably where by this time that you've cleaned up things there, you've probably also, according to the textbook, you've probably taken care of other problems too. All right, so functional dependencies. Let's take a specific example of this table, so an instance of it, and let's just take a look at what we're talking about. So you've got ID, name, level, wages, hours. All right, so we've got 4 employees. My favorite, my Bob, my Mary, Fred, and Beth. And Bob's a level 5, Mary's level 8, Fred is a level 5, and Beth is a level 8. Because level determines wages, we know that when they're 5s, they're getting paid $15 an hour, and when they're 8s, they're getting $21 an hour. And let's just say Bob only works 30 hours a week. Mary is scheduled for 35. Fred puts in a long 40, but Beth is a 35. All right. They must have some sort of flexible arrangement here. That's great. Now, so that's our table. Now, this is it. We don't have some other table somewhere that records for us level and wages. When we designed this database, we thought, I don't know why, but we thought, let's just do it like this. Okay. And then we notice that we have some problems here. We've got redundant data. What is redundant? All right. We keep storing over and over this information. So every time that we have a 5, we write 15. Every time we have an 8, we write 21. I mean, and it goes on. Imagine this table goes on for all the employees and for all these different levels. It's just like, okay. So now with this redundancy, we've got a real problem. All right. So let's think about if we want to do an update. What sort of problems do we have with our update? Let's say we want to change the wages for a level 5. Let's say if we update Bob, raising it to $16 an hour. But if we don't go and hunt down all the other level 5s and also change them to 16, now we'll have an inconsistency in the database. It's not just that Bob got a raise at this company, the level determines the wages. And so if we changed it for Bob, we have to find everyone else who does it. And you might say, oh, that's easy. I'll just do that in my update statement where, level is equal to 5. I'm going to update the wages to 16. Fine. Yeah. But we do have the potential to make a mistake. All right. And that's what we want to avoid. What about our insert problems? Well, let's say we bring in a new hire. Well, we can't add anyone in here unless we already know their level and wages. And that's, and likewise, their hours. But, you can't add an employee without adding the other information. But we certainly could envision that we might really want to be able to be like, oh, yeah, we got a new employee. Great. Oh, we're waiting on someone to tell us what their wages are, but we need them in here for, to issue them a photo ID or something. Okay. Same problem. Same thing. What about deleting? Well, all right. Let's say we get rid of Bob and Fred. They both decided to quit in tandem. And if this was the only data we had, actually, we could lose entirely the mapping between level and wages. In other words, we have encoded this information of level goes to wages in this table. Sure, it gets repeated a lot, but if we delete all the rows that happen to have a particular part of the mapping that we care about, it's gone. It's no longer stored in our database. We've lost that information. All we wanted to do was get rid of Bob and Fred, but we've also lost a part of our mapping, and that's a real problem. All right. Now, redundancy of all sorts can cause this problem, not just functional dependencies, but functional dependencies are a real serious source of this issue. Where we have these functional dependencies, we're inevitably going to be having, if they're the wrong sort of functional dependencies, we're going to be having problems with redundancy. So let's take a look at getting rid of these functional dependencies. All right, let's first deal with a definition then of what a functional dependency is. That's the idea. This comes from the cow book. We'll say an instance R of the relation. This is the big R is the relation. The small r is the instance. Remember, instance is putting data into a table, putting it into the relation. So an instance R of R satisfies the functional dependency again, abbreviated FD, drawn with X to Y, if the following holds for every pair of tuples. T sub 1 and T sub 2 in R. So if T sub 1 dot X is equal to T sub 2 dot X, all right, and this is what's missing from here is explaining is that this is attribute X, this is attribute Y, and in fact, it could be attributes X and attributes Y. It doesn't have to be a single attribute. It can be multiple attributes. We could have a set of attributes of R and a set of attributes of R of Y. such that we have a functional dependency between these attributes and those attributes. Anyway, so it's easy enough at the moment to think of them as single attributes x and y. So if t sub 1 dot x is equal to t sub 2 equals x, then, and this is the functional dependency part, then t sub 1 dot y is equal to t sub 2 dot y. Okay, basically, look, if we know x, so if we know this attribute or a set of attributes, so if we know its value, whatever its value is, then wherever that value is, we know what y is. So it's basically saying for all tuples, if we know what x is, we know what y is. X is said to determine y. That's just what we were looking at on the previous example. Oh, this level determines what the wages are. Okay, and so we can think about this and look at this. And now we're going to see, where do we see functional dependencies in our tables? And let's start identifying different types of them. And as we identify different types of them, we'll understand how we're progressing through our normal forms. The first type of functional dependency to consider is known as a partial functional dependency. All right. And this is basically, we let x be a subset of attributes of relation R. We'll use this x and a and r throughout all of our examples. And a be an attribute of R. So in our examples, we'll let A always be a single attribute. We'll let X be a subset, a set of these attributes. In the most general case, yes, we can have X and A both be multiple attributes. But for all of our examples and everything we're going to talk about, we're going to follow the cow book and have this be multiple columns and this one be single columns. All right, so then what is a partial? Given a functional dependency, X determines A if X is a proper subset of a candidate key this is known as a partial functional dependency. So in pictorial form, we have some candidate key. We have some attributes, which are X. They are a proper subset of the key. So basically, look, we've got some columns for the key over here, and we have some more columns for X. So there's some attributes and some more attributes. All of those attributes together form the candidate key. So X is a subset. The columns that make up X, the attributes that make up X, are a subset of all the attributes that make up our candidate key. And you might go, oh, what is a candidate key? We got these super keys, candidate keys, and primary keys. Super keys is any set of columns or attributes that can uniquely identify the rows in our table. But they're not a minimal key. In other words, there's some column or multiple columns in a super key that we could remove, and we will still be able to uniquely identify the row in the table. If we have a key that we cannot remove any of the columns from to identify a row, that is a candidate key. They're called candidate keys because it's from that set of keys that we as designers pick what should we choose as the primary key. It's one of the candidate keys that we choose, and when we create a table, we say that's a primary key. All right, and remember, we can have multiple candidate keys then, and certainly lots of super keys. I mean, a super key includes just simply saying, yeah, I'm going to take all the attributes, and that will uniquely identify that row, and identify a row. Anyway, so we got this. Let's draw our dependency. We've got attribute A over here. All right. And so this determines that. So these attributes here determine attribute A. Because it's a proper subset of the candidate key, we call it a partial functional dependency. These are just definitions, okay? And so if we are in first normal form, and then we look at our tables and we see that there are no partial functional dependencies, then we know we are in second normal form. So that's just definition. You look in the book and the books will say, this is just of historical significance. Let's move on. So let's move on. All right. Now the next one, our goal now is to make ourselves to third normal form. So remember, we've got this x and the a. X determines a, that's our functional dependency. So if x is not a proper subset of any candidate key, then we have a transitive functional dependency. All right, so you can have some key, and you have the attributes which determine what x are, and they could overlap with key, but x is not a proper subset. X, by the way, can even be out on its own. It doesn't have to be overlapping with the key. And then we've got our attribute A. So x determines this, but the thing that makes it transitive is the key determines what the settings of x are. So when we look at a table, and if we notice, we've got our candidate key, and then we've got these attributes x, some of them which are not part of the key, and these determine what happens here with this attribute. That is a transitive functional dependency. There is another way to have a transitive functional dependency, is actually to go and you can have your key and you can put A inside of it, and your attribute x can be outside of it. All right, or the attributes for x can be, and then the key can determine what x is. Same thing, the key is determining x, and then x can determine back what A is inside of, which is part of your candidate key. So these are the two ways that we can have a transitive functional dependency. And this leads us then to, we get to say, well, if we are in second normal form, which again was we were in first normal form, and we had gotten rid of all of our partial functional dependencies. So if we've made it to that stage, and then we go, oh, if we're in that, and now we can see that there are no transitive functional dependencies, then we've made it to third normal form. What's the message here so far? The message here is we got to look at our table, our relation that we've created, and go, where are the functional dependencies? Do I see things that depend upon one column or a set of columns, which will always tell me what the value is in another column? If so, I have a functional dependency. Oh, now what type of functional dependency is it? Is it a partial? Ooh, I'm not even in second normal form. Is it a transitive? Ooh, I'm not even in third normal form. Okay, but oh, let's see. I've got functional dependencies, but I have no partial and I have no transitive. Ah, okay, so I'm in third normal form. That's great. Could I be even better? Could I sign up for a new badge, a new qualification? The answer is yes. The next one up is Boyce-Codd normal form, which is, they refer to it in the book as sort of like a refinement of third normal form, which I think is kind of fitting given that they stuck it in between third and fourth. It's kind of like, here's a better version of third normal form. So Boyce-Codd normal form, usually abbreviated BCNF. All right. So again, this is definition from Cow book. Let R be a relation schema. That's the same thing we've said before. We're going to say, we're going to let F be the set of functional dependencies given to hold over R. Now, where are we going to figure out what this set of functional dependencies is? By using our knowledge of the data that we are modeling and knowing, yeah, whenever I have this value here in this column, I'm guaranteed that I'm going to have this value over here. And it's always the case. If I know this, that determines this. I have a functional dependency. And you can go through and you could come up and figure out what all of your functional dependencies are using your knowledge. There's no way for the system to say, I see your functional dependencies. Now you could load up a database with data and say, in this table, what do you diagnose and recognize could be functional dependencies? As in, you see that every time this attribute has this value, this one has this value, you could identify potential functional dependencies, but it just might be that the data isn't complete yet. And it could just be a coincidence that you have a functional dependency there. So you can't really tell from the data. It has to be knowledge that you have. Anyway, so we got this set that we figured out to hold over R. And we're going to let, again, X be a subset. You're kind of repeating things to get this full definition of attributes of R. And we're going to have A be an attribute of R. So the only thing new here was this introduction of F. All right. So let's get to B, C, and N, F. So the relation R is in B, C, and F, Boyce-Codd normal form, if for every functional dependency X determines A in the set F, which is the set of all the functional dependencies over our relation, one of the following statements is true. So we either have A is an element of X, which basically says that is, it is a trivial, I don't know why I'm having trouble spelling trivial, trivial functional dependency Now I'm going to pause, and you're like, trivial functional dependency? You didn't define trivial functional dependency. A trivial functional dependency. So A is one of the columns of X, is one of the attributes of X. So let's see. I have all these values, and I'm saying I've got this these columns, and one of those columns is A. And you know what? Oh my goodness gracious. Every time I see A has that value. It's like every time I see Mark. It's a trivial functional dependency. Like, yes, column A depends upon column X because column A is part of X. It's trivial. It's like, who cares? All right, that's not a functional dependency we care about. So the big thing here is X is a super key. Now, in Jennifer Wyndham's videos, she's like, you're going to see some books say super key. You're going to see some books say candidate key. You know, the real thing is, you can easily just replace this if you want in your mind with candidate key. I mean, the full definition is X is a super key. But the reality is that we could trim X back because it is a super key. It means it has superfluous, has extra attributes in it that we don't need to uniquely identify a row. What really is critical about saying it's a super key is that somewhere inside of it is a candidate key. And so what we're really looking for is when we are looking at these functional dependencies in F, we want to find out that they're all trivial, which we're not even going to pay attention to. So what we're really looking for is, do we have all of our functional dependencies basically such that they're a candidate key? They can be this functional dependency that we see in this table is actually the candidate key. And if you think about that, that sounds really nice. Oh, this property, this candidate key that uniquely identifies a tuple, is what determines then what these other attributes' values are. Oh, so if we think about it, it's like, yeah, the primary key that says I have Mark here determines what my eye color is, what my hair color is, how tall I am, all my attributes. Yeah, it's because it uniquely identifies me, and these are my attributes, and that if you know who I am, you know what my attributes are. And that would be, and if that holds true for all the attributes in the table, it's kind of really nice. Now we know that we've got this nice primary key, which, because we've picked the candidate key. Oh, and the candidate key is the thing that determines what the values of the attributes are. The attributes don't determine each other at all. It's all rooted back to being able to uniquely identify the row. That's what Boyce-Codd normal form gets us in, which, again, think about when you're doing your entity relationship design. That's what you're aiming for. I have an entity. Again, I'm an entity. I'm going to have some way to uniquely identify it. I'm going to come up with some primary key for it. What are the attributes I want to model for that entity? Great. And I'm going to have them be atomic and stuff. And okay, before you know it, you're likely to have chosen attributes for an entity that, given the entity's identity, some way to identify it uniquely in the table, that's the only thing that determines one attribute from another, okay? It's not that, oh, I know Mark, he's got, I don't know, brown hair or something like that, brown and gray or whatever. Therefore, it determines, his shoe size. I don't know. And again, the attributes aren't going to tell you about the other attributes in a perfect mapping. Sure, you might have correlations and statistics and stuff, but we're talking about, if I know this, I always know that. The only way that you know what something is guaranteed is based back on the candidate key. That gives you Boyce-Codd normal form, and that's the cool part of all of this. So let's state that in a slightly different way. We're going to state it a couple times to help explain it. Is first, we're going to draw our drawing. So we got our key. And again, this is our candidate key. And then we have, something that's a non-key attribute, one, and another non-key attribute. So these are attributes that on their own cannot be used as a key. They do not tell us about the row. Basically, this continues on. All right, and the key determines this one, and this one, and all of them. All right, and the cow book says it's got a quote from a person named Kent, and I actually looked, and it looks like the references are wrong. I'm not quite sure. I was a little confusing, but I'm just going to stick with what they said. It's from Kent, whoever Kent is. That would be a last name, not a first name. They say, it's this. He or she has this neat way of saying each attribute must describe, and I really like that notion, describe, because that's what our attributes are for our entities, our descriptions. And then they actually, obviously, he's left this out and they've added this, must describe an entity or relationship identified by, so the little thing they stuck in here, an entity or relationship identified must describe the key, the whole key, and nothing but the key. So what are we really saying here? Well, so it must be by the key. So this is really sort of the attribute must describe an entity or relationships identified by the key. So the key is identifying these dependencies. So basically, there are no other functional dependencies. The only functional dependencies we have go from the key to our attributes. Our attributes don't have any dependencies between them, and our attributes don't go and have some sort of, partially notion of dependency back to some part of the key. So it's the whole key. This is, none of these, no partial FD. So we don't have a part of the key depending on it. It's the key tells us what is determined there. Okay, and nothing but the key. And again, this would be like the no transitive part. It's the key that does it. It's not that we go around and hop around with our attributes. Now, to me, when I read this and translate this, I think this is the thing to think about when you go back to your entity relationship design. Is you're going to say to yourself, all right, I've got an entity. I'm going to figure out what's a good primary key for it. And then all of my other attributes I'm going to make for it. I'm going to make sure that the only thing that determines what their value is my primary key. Okay, or a candidate key. So you could actually have, again, more than one candidate key in a table. So you could absolutely have times where, I could choose this column or that column or the set of these columns, and those are all candidate keys. But so long as it's the keyness, the thing that identifies uniquely that row, if that is what then determines what the values of the attributes are and nothing else, the other attributes don't determine each other, and there's not some sub part of a key, we're going to be good. So when you do the entity relationship design, it's at that stage that you say to yourself, hey, am I basically doing this thing? Am I making this sort of notion that and these attributes only are tied back to my candidate keys, whatever my candidate keys are in the table? If so, I'm good to go. That's excellent. That's great. There's nothing else that determines it. I know that when I'm done, I'm going to be in Boyce Codd normal form. And that's the really nice thing. Another way that this is put is to say, to be in Boyce Codd normal form, if an attribute A is not one of the attributes of X. Remember, X is determining A in these definitions. Then X must be a key if we have a functional dependency, X determines A. So look, got A, and it's not part of X, but we have X determining A, then X has to be a key, okay? If it's not, we're not in BCNF. All right. So where do we go from there? Well, there is very nicely, this is sort of the cherry on the top of the sundae. If you wanted to, instead of just figuring it out and going back to your relationship diagramming and trying to eliminate your functional dependency, you could actually apply an algorithm to do the decomposition. All right. So the idea here is decomposition means let's break our table up into two tables or more tables such that we remove these functional dependencies. So this algorithm goes as follows. So X is a subset of R. We know that X determines A is a functional dependency that we've identified violates BCNF. In other words, we have found when we look at our table that we have a functional dependency where X is not a candidate key. All right, so what we're going to do is we're going to decompose to break apart the relation R into R minus the attribute A and XA. We're going to put X and A together, and we're going to remove A from R, and these are going to give us two new relations. Then we continue with our algorithm. We have to look at these. If R minus A or XA is not in BCNF, so in other words, if they have a violation that's in them, then we decompose them by the fancy term recursive application of this algorithm. But basically, go back to step one, but plug in these guys, whichever ones violate. We have to keep doing this until we finish. All right, so, we found that we've got something that's violation. Okay, break it up like this. Now check them. If they're in violation, go back here and fix them up and keep repeating this until done. All right. Let's say we had done something really crazy. I think it's really crazy. we had come up with a table where we did, let's say we had put, for whatever reason, we called this our books relation, and we put book ID and then a title, and then we put an author ID and then the author's name. Okay, so you look at this. Where do we see functional dependencies? Well, first of all, where do we have candidate key? So book ID and author ID are what we are going to need to uniquely identify this row. That's our candidate key. We can't get rid of one and still be able to identify the row uniquely. So this is what we're going to have. This is a setup where, again, what's going to happen here is you could have multiple author IDs for a given book ID. Okay, so we could have multiple authors of a book. Is this what this table would allow us to have? But we're going to see redundant data, aren't we? Because we're going to repeat authors' names all over the place. We're going to repeat titles all over the place. So we've got quite a bit of redundant data. What are our functional dependencies that we're going to be worried about here? Well, let's take a look. Everywhere where we have a book ID, that will tell us what the title is. Everywhere that we have an author ID, that will tell us the author's name. Okay. We could look at and talk about others, but what we're concerned about is these would be in violation. These functional dependencies would violate B, C, and F because book ID by itself is not a candidate key, and author ID by itself is not a candidate key. We'd need both, but all we need for the title is the book ID, and all we need for the author is the name. And so we apply this algorithm, and so we say, let's start with this one. So we're going to say this is X and this is A, and so we're going to have a new relation, which is book ID and title, and then we're going to take this one and we're going to break it into a relation where we keep book ID and everything else. Oh, not title, sorry. Get rid of title, that's the A. Then we have author ID and name. So now we've gone from this to these two relations. We look at this one and we've got this as a functional dependency that's in violation. Because again, this is the candidate key. All right, but author ID is all we need to identify name. So we go and we do this again. So this will produce a new relation, author ID and name. And the final one, we have a book ID and author ID. This is, we no longer have this one. We no longer have this one. We're left with these three relations, and what we actually see is, so this is an entity set, this is an entity set, and this is a relationship set. So it doesn't always work out all this beautiful. This is an example to illustrate that it can work out really nicely. I think it's much more important to, as we're going and doing our entity relationship design, we basically say, yeah, look at that candidate key, look at the candidate keys, and if those are the only things that determine the other attributes in the entity set, we're going to be good. And we're not going to need to go any further because we will know then that we are in Boyce-Codd normal form. All right.